There is a tectonic shift underway in chip making. One so big, it's not just about factories. It's about who controls the global economy itself. Let me show you. Just a few years ago, the Arizona desert was nothing but dust. Fast forward to today, and the same land holds America's most ambitious project. TSMC's most advanced chip factory. $165 billion bet on the future of microchips. There is a reason why TSMC chose Arizona. The desert offers one advantage Taiwan can't match: almost zero risk of natural disaster. And that stability matters when the stakes are that high. The plan sounded simple. Just copy a semiconductor fab from Taiwan into the US soil. But this turned out to be way harder than anyone ever expected. In Arizona, TSMC ran straight into a sandstorm of problems. Because chip making at the nanometer scale isn't about construction. It's choreography, equipment, chemicals, and people moving in a perfect lockstep. Get it right, and you are printing money. Miss just one step, and billions go up in smoke. And here is the irony. The US invented the semiconductor industry and still leads in design, equipment, and software for chip design. But manufacturing dominance slipped away. US share of chips fell from 40% in 1990 to about 10% today. Can TSMC bring advanced chip making back to the US? Subscribe if you're curious, and let's get into it. On paper, the plan is simple. In reality, it's brutal. In Taiwan, TSMC can build a fab in just 2 years. In Arizona, every single step took at least twice as long. So, what happened? I've been working in semiconductor industry for the last 10 years. And my main lesson is chip making is the art of killing variables. Now, consider this. At 4-nanometer process, there are hundreds of variables spread across 4,000 manufacturing steps. And here is the catch. Any of them can kill a chip. And variables don't behave the same in every place. In Taiwan, TSMC tuned the recipe for local water, air, power, suppliers, and even culture. Move the fab to Arizona, and all these variables shift. Arizona is not known for water. Air is different, and most important, the culture is very different. Even the ground is different. Here, the ground is much drier, with rock-hard layers beneath. That gives it a higher natural frequency. Any of those shifts can throw off nanoscale precision, which is enough to kill an entire chip. Now multiply that across thousands of wafers, and suddenly production yield drops. Yield is critical. It's a percentage of chips per wafer that actually function. At 90% yield, like TSMC achieves in Taiwan, you're practically minting money. At 30%, you're bleeding cash. But in Arizona, instead of glory, there was chaos. Variables drifted. Dust storms breached clean rooms. Every system was pushed to its limits. Yield collapsed. The truth is, you can ship in equipment. You can even fly in engineers from Taiwan, but you cannot ship the context. And here is a hidden truth. Each time you want to build a semiconductor factory, you're not just building one. In fact, you have to build 4 factories, 4 invisible factories inside. The first invisible factory inside the factory is the water plant. And in the desert, this is the hardest battle of all. You might be surprised, but at the bleeding edge, water matters as much as the famous EUV lithography machines. And that's the problem, because semiconductor manufacturing uses a lot of water. While Arizona is one of the most water-stressed places on Earth, the state depends on the Colorado River, which is already stretched to its limit. At the same time, Arizona hosts more than 100 active data centers. And this includes massive data centers run by hyperscalers like Meta and Microsoft. These facilities consume enormous amount of water for cooling. The irony is brutal. Those same data centers burn a lot of energy, and power plants again use water to generate this energy. That electricity turns into heat inside the servers, which then require even more water to cool them. It's a feedback loop with heavy consequences. As you can see, the water situation there is already a nightmare. And now this new fab will attempt to draw on the same finite supply. But a semiconductor fab is not just thirsty for large quantities of water. It requires ultra-pure water. That's 1,000 times cleaner than drinking water, and even cleaner than the one used in medical injections. Because a single contaminant or particle can destroy a $30,000 wafer. Water is a backbone of semiconductor manufacturing. It touches nearly every step of the process. After etching, it rinses away acids. After photoresist, it strips away chemicals. Just imagine, even in immersion lithography, water sits between the lens and wafer, sharpening the image. And the amount of water used is quite shocking. Each and every silicon wafer drinks around 2,000 gallons of water across its lifetime. This means Fab 21 alone will consume more than 4 million gallons. That's about 6 Olympic swimming pools of water per day. In Taiwan, TSMC cracked this by building dedicated water plants, purifying and recycling every possible drop. But in Arizona, water is different, chemically different. It's full of magnesium and calcium. You can't just copy-paste the solution from Taiwan. So, how do you get that much pure water in the middle of desert? The answer is hard. You don't just build a semiconductor fab. You have to build a dedicated water plant of the size of a stadium. Inside, water flows through stage after stage. Filtration, reverse osmosis, and deionization. And even after all of that, tiny impurities still remain. Then comes the final polishing. Resins and ultrafilters scrub out the last traces, leaving water so pure it exists only in semiconductor fab. And TSMC had to rebuild this entire system for the unique chemistry of Arizona's water. What comes out is the purest water on Earth. And the genius of the water fab is that instead of dumping waste, the plant recycles it, making sure their hard-earned investment doesn't go down the drain. Literally. If, for some reason, it can't be reused again, it gets redirected into cooling. That's how Fab 21 reduces its draw on city water, while still feeding one of the most water-hungry fabs on the planet. Soon they realized water wasn't enough. Another critical cleanser in chip making is sulfuric acid, the quiet backbone of the fab. It strips photoresist, clears residues, and burns away any trace of contamination, so the next layer can stick. It's not glamorous, but without sulfuric acid, the fab stops cold. And not just any acid will do. Again, it has to be ultra pure. And that's where Arizona hit the wall. US vendors were able to make clean acid, but local prices were nearly 5 times higher than in Taiwan. So TSMC had to ship it 6,500 miles from Taiwan. And as crazy as it sounds, it was still cheaper and more reliable than buying locally. Of course, that couldn't last forever. So the supply chain followed. Sunlit, a Taiwanese chemical giant and one of the key TSMC partners, had to build a new plant in Phoenix. Again, not a copy-paste factory, but one attuned to Arizona-specific water and desert conditions. And that move was critical, because copying a fab means copying its suppliers too, and planting them next door. If acid is a backbone, then gases are the lifeline of a fab. And not just oxygen or nitrogen, but gases like neon, rare and tough to source at the ultra-high purity chip making needs. Neon is critical for the lasers used in photolithography. It makes up about 95% of the gas mix inside deep ultraviolet tools that print chip patterns. EUV handles the most critical layers, the interconnect, but DUV still prints the most of the stack. The fact is, DUV can't run without neon. The catch here is again, it has to be ultra pure. I know I said it already 3 times, but that's the fact, the truth of chip making. Everything has to be cleaner than clean. Even a trace of impurity destabilizes the laser, blurs the light, and seeds tiny defects that collapse the yield. And again, Arizona comes up empty. No local supply. For now, only a few essential gases used in chip making are produced locally in Fab 21. But most of these specialty gases are still imported from Taiwan, Japan, and Europe. That's the fragile truth. And even the silicon wafers themselves are still shipped from Taiwan and Japan. So, from the outside, Fab 21 looks American. But under the hood, it's still tied to a supply chain stretching far, thousands of miles across the oceans. And that reminds me of something closer to home. These days, we are all juggling different AI tools. One for writing, another for research, another for emails. And just like with fabs, when you source it all from everywhere, the complexity adds up in time and in money. That's why I've been using Merlin AI. It's all-in-one AI tool that brings together the best AI models all in one place. In my workflow, it's super useful for summarizing dense research papers, or fact-checking, or even scripting videos like this one. While ChatGPT Plus is $20 a month for just one single model, with Merlin you get all of them in one place for about $5 a month, with my 75% off code. If you want to try Merlin AI, click the link below or scan the QR code here and use my code AN5 at the checkout. This code will magically bring price down to about $5. This discount is valid for a limited time only, so check it out right now, and thank you, Merlin, for sponsoring this episode. Water is one challenge, but what about air? You might think, surely, Arizona has plenty of air, right? But that's the most fragile ingredient in the recipe. And once you get into a semiconductor fab, you will immediately realize why. Back when I was doing my master thesis, which was now approximately a decade ago, I used to go inside the fab, inside the clean room, because there was something wrong going on with my chip and I had to go and watch the whole process to figure out what's going on. That's when I first saw how extreme these environments are, because the obsession with cleanliness is beyond imagination. Basically, you are wrapped head to toe in a clean room suit. The rules are absolute. Nothing escapes your body into the air. Even a single eyelash drifting onto a wafer can destroy weeks of progress. Clean rooms is the place where the chips really get their crunch. Fab's 21 clean room is enormous, about 160,000 square meters or up to 1.7 million square feet. By size alone, it ranks among the largest clean rooms ever built. But the bigger the room, the harder it is to keep it pure. And the Arizona desert makes it even tougher. Clean air is constantly pushed from the ceiling, flowing smoothly over the machines, then slipping through vents in the floor. And it's all about pressure, because the air pressure inside the clean room is kept slightly higher than outside. Dust and particles from the desert can never be permitted to leak in. TSMC flew in teams from Taiwan to fine-tune airflow until it was perfect. Just imagine, outside there are thousands of particles, while inside the fab, inside the clean room, it can never rise above 10 particles per cubic meter. It's fascinating because the fab literally breathes outwards and pushes the desert away. And once the air is finally under control, the next challenge begins. The tools arrive. And this is where the real money shows up. 70% of a fab's cost isn't concrete or clean rooms. It's the machines. Billions of dollars worth of tools, packed wall to wall. And this is an area that really plays to America's strength. Companies like Applied Materials, Lam Research, and KLA cover most of the critical steps in chip making. Getting that equipment to Arizona was an easy part. But one thing the US doesn't have is lithography. The most advanced tools, EUV and DUV scanners that print chip patterns on the wafers, come from ASML in Netherlands. Without these tools, no fab, not even TSMC, can print chips at 5, 3, or 2 nanometers. The United States lead in etch, deposition, process control, but they still have to import EUV machines from Europe. Moving these machines into the fab is a stressful process, because if you tilt a component even slightly or drop a part, the precision is ruined. Importing and installing EUV machines is a stressful job. Just one mistake, and the fab goes dark before it even starts. TSMC's Fab 21 needs not one, but dozens machines worth $150 million each just to get started. And once it's all in place, you realize something else. Actually, building a fab was the easy part. The real challenge is what comes next. Getting these machines to work together seamlessly, flawlessly, to crave the tiniest transistor features into silicon. This is pure art. Imagine it's like conducting an orchestra where every single instrument costs $150 million and plays at the scale of atoms. Here, the real battle for yield begins, because the fab doesn't make any money before the wafer comes out clean from defects. And the first wafers never do. The equipment is new. The process steps are new in the new environment. So engineers, operators, and even tool vendors work together day and night, tuning, adjusting each of 1,000 steps it takes to build a modern computer chip. And the scale is brutal. At 4 nanometers, a single wafer stacks more than 80 layers across 4,000 process steps. It takes months and thousands of tweaks before the first wafer finally comes out right. This is the first 4 nanometers wafer manufactured at Fab 21 in Arizona. The most advanced silicon wafer ever made on the US soil. It's progress, but that only happened after going through a lot of pain. Output is still low, covering only about 7% of the US demand. And costs in Arizona are at least 50% higher than in Taiwan. Why? because almost all raw materials, from chemicals to wafers, are still shipped in from abroad. And that's quite surprising, because Intel's most advanced fab, Fab 42, has been sitting just 30 minutes away for more than a decade. Yet most of its materials still come from abroad. Now, TSMC is trying to rebuild the entire supply chain here locally in Arizona. And in the desert, engineering talent is even scarcer than water. Taiwan's real advantage isn't just fabs, it's people. Generations of engineers trained in the rituals of chip making. But here is the harsh truth. Why it is in fact so hard to build a semiconductor fab. Because yes, you need machines and chemicals and ecosystem, but the breakthroughs don't come from machines. They come from people. This is the invisible web that holds it all together. Engineers who know how to fine-tune every process. Suppliers who can deliver pure chemicals on time. And service teams who can bring a $150 million EUV machine back to life at 3 a.m. without stopping the line. In Taiwan, this skill set has been built over decades. Arizona had none of that. So they started to fix this gap. Local colleges started to create semiconductor programs. TSMC started to send engineers to Taiwan to give them the opportunity to absorb the culture of extreme precision. Because chip making at the bleeding edge isn't just knowledge, it's a habit, muscle memory, and slowly yield began to climb. By January this year, Fab 21 finally reached mass production of 4-nanometer chips, with yields now reported as comparable to TSMC's fabs in Taiwan. That means this complex choreography is finally clicking. Water, air, wafers, assets, tools, and even people all moving together in a perfect sync. This is a true milestone. By 2028, this fab is set to grow to a mega fab, cranking out 100,000 wafers a month. For the first time in decades, America is able to produce bleeding-edge logic chips built domestically. It's a breakthrough and warning at the same time. You saw it yourself. These chips are expensive and still dependent on a long supply chain. Output is still a fraction of what is produced in Taiwan. And packaging, it still flies across the Pacific, because the chips like NVIDIA GPUs, which are built in Fab 21, literally sent back to Taiwan for the final assembly. The reason is simple. The US doesn't have advanced packaging capacity yet, especially for chip-on-wafer-on-substrate packaging. And this one is critical, because it allows to place multiple dies side by side on a single interposer, basically allowing you to put high bandwidth memory right next to the GPU cores. That's why every NVIDIA GPU, including the new Blackwell GPU, depends on it. And for now, this packaging can be only done in Taiwan. The long-term goal, eventually, to bring this packaging in-house on American soil. The biggest challenge of Fab 21 is that it will be always behind the Taiwan by 1 or 2 process nodes. And the logic is simple. Taiwan develops, Arizona inherits. Every new process node, let's say 1.6 nanometers, starts in Taiwan. The R&D center runs the pilot line, often with the yields below 30%. Then the work shifts to the mother fab, where yields are pushed up and the process is stabilized. Only once it's mature, they transfer it overseas. That means Fab 21 won't invent new nodes, but it will take on the critical ramp-up. This model lets TSMC to expand globally without losing efficiency. But the goal is even bigger, to eventually build a mother fab in the US as well. And it's impressive that despite all these challenges, TSMC still pushed through. The 1,100-acre site is designed for up to 6 fabs. 3 are already underway, alongside 2 advanced packaging facilities and an R&D center. Together, they will form a start of a full semiconductor ecosystem right here in the desert. The first fab, Phase 1, is already ramping up the production of NVIDIA and Apple chips. Phase 2 and Phase 3 are planned for 2026, targeting the next generation 3nm and 2nm process nodes. But Fab 21 isn't enough. We need more fabs, more scale, more engineering talent. And that's why I think Intel matters so much. Intel Foundry isn't just another business unit. It's the most important part of Intel, and it carries massive strategic value for the United States. What is interesting, Intel's Fab 42 is actually 25 miles away from this new TSMC fab. Today, it manufactures 10nm class technology, and it is set to ramp up the production of Intel 7 and Intel 4 nodes. But the bigger play is what comes next. Intel 18A, which is designed to compete with TSMC's A16. Both of them will use the new gate-all-around transistor architecture and backside power delivery. You can see now why Intel has struggled. One of the reasons, on top of everything we've discussed, that fabs are just too expensive, and this financial gravity pulled everyone else out of this tough race. For a foundry to be profitable, you need to have massive wafer volume just to pay off the billions invested. At the bleeding edge, only TSMC and Samsung have the capital and scale to make the economics work. Will Intel be able to catch up? Only time will tell. For the US, the CHIPS Act is just the beginning. To really compete, they need to streamline approvals, so fabs don't take a decade to build. And most importantly, they have to support semiconductor startups. After all, it was Silicon Valley startups that created the whole modern semiconductor industry. And the next step is to fix the talent pipeline, means inspire new talent and build this whole cultural prestige around semiconductors. This was actually the mission of my channel from the very beginning. Back then, nobody was talking about semiconductors, and as a chip designer, my goal was, and still is, to bring more young talent into the industry so we can push it forward together. And if you believe in this mission, support me by sharing this video with your friends and colleagues. Fab 21 proves something very important. It proves that you can't just copy a semiconductor fab. You need to build 4 custom factories in one. A factory for water, a factory for air, a factory for tools, and a factory for people. And then even a factory for power, which we haven't discussed yet. Get one wrong, just a little bit, and the whole system collapses. And Arizona showed just how brutal this can be. This time, TSMC has given America a foothold. Will they be able to turn it into a powerhouse? We will find out soon. You've been watching Anastasia in Tech. This episode was a lot of work. If you enjoyed it, subscribe to the channel and connect with me on LinkedIn. You can find all the links in the description box below. Thank you for your support, and I'm gonna see you in the next one. Ciao!